One, is it good morning? Yes, it's still good morning. Try to keep track of the days. We are going to be looking at a new section today. We'll get it started today and we'll get it finished on Friday. And it's section 8.2, and we're going to get what is called the surface area from revolutions. And so what exactly happens here, and I'll bring this back in a minute, is that I want you to, this is one example of how you would calculate this. I want you to imagine that you have a function called y equals f of x, and it starts off at a value of x at a and it finishes off at a value b. And the revolution or rotation part comes in here. You take that line, and just like we did in volumes of revolution, you rotate it. I believe if you rotate this shape, would you agree it looks a bit like a bell? Would that seem reasonable, right? So you take the function y equals f of x, you rotate it about the x-axis, and you get this solid shape called the bell. The surface of revolution also called the surface area, is the area of that outside thing. So can you imagine you were wanting to paint the outside of that bell? How many square feet of paint? You know, because if you look at paint, it says it's 200 square feet, right, or 400 square feet. That's what you can get, right? So think of covering it with material, if you want to think of it in that sense, right? How many square yards of cloth would I need to cover only the outside part of that bell? And that's what we're going to be finding. And there are 4 situations. Each situation has a specific formula that will calculate the surface area. Right, 4 situations. I'm going to be putting this video up sometime this evening. There is far too much, I would say, there's far too much for you to bother to write it down right now. So we'll just talk about the 4 situations, and then as I need them, I'll bring them up and you can check them out. Right, the first situation and the second situation have in common that you're rotating the shape about the x-axis, right? So imagine the curve being rotated about the x-axis. If the function is of the form y equals f of x, with x between a and b, then you're going to use this formula here. It's the integral from a to b, 2 pi f of x, the square root of 1 plus the derivative of f squared dx. If, however, you're still rotating the curve about the x-axis, but your information is given as x equals y cubed, right? Or x equals y squared plus y, right? That format. And that the y goes from c to d. You can still take that curve and rotate it about the x-axis, right? It's still a curve, so you can rotate it. And the formula for calculating its surface area is 2 pi y, the square root of 1 plus the derivative of the function squared dy. Now you notice that these are not the same. They're similar, but not the same. For each situation, you have to make sure that you use the correct formula, otherwise you won't get the right answer. So if you're rotating about the x-axis, these are the 2 guys you're going to use. The top one, when everything's using x's, and the second one, when everything is in terms of y, right? X equals y cubed, y from 1 to 2. And then over here, 2 more situations. Now we're taking the curve, but we're rotating it, right, horizontally, right, vertically, I should say, right? We're going, rotating it about the y-axis. And if all the information is in terms of x's, you use this formula, 2 pi x, the square root of this. And if everything is in terms of y, you use this formula. So you're going to get a story. It's going to be a curve. It's going to get rotated either about the x or the y-axis. And in that story, the function is going to be y equals x cubed or x equals y squared. And from those two pieces of information, one of these two formula gets used. And so your job is to know which one gets used in which situation. Before we actually start doing some questions, if I cover up all of this and say, do you recognize the square root of 1 plus the derivative squared? Where have you seen that guy?
Arc length.
It's arc length. Haven't you seen 2 pi f of x dx somewhere? If I cover this up, have you seen 2 pi f of x dx somewhere? Where would that be? Where did you see 2 pi f of x dx, or something similar to that?
Volume.
In a volume, right? There's a missing x in it, but essentially, can you imagine then what's happened here is that they've took an arc length formula, a bit of it, most of it, and a bit of the volume formula and made this monster that actually does a job. It gets you the surface area. So it's not a proof that these formula work, but do you get a kind of feel for where they kind of got them from? And of course, like everything else, you can go online and you can see a proof for those people who it helps them to understand what's going on. So there are going to be 3 situations algebraically that's going to happen. Don't matter where it comes from, but you're going to get questions that look like this. Okay. You're going to get questions that end up nice and look like that. What technique will you use to integrate questions that look like this? What technique would you use to integrate that guy?
U substitution.
And would you agree that 4 plus x cubed is the go-to guy, right?
Yep.
So if you ever see a combination like this, right, that's the way you're going to go. Suppose you see something like that. You could actually do it 2 ways. Couldn't you do a U sub? And for some of you, that might be the best way to go. If I rewrite it as 2x plus 1 to the half, couldn't I do also the linear shortcut method on it? And the third one is going to look something like this. Forget about this bit. That's not an issue. This is the issue. Sometimes you're going to get a square root with 3 things in it. How do you deal with questions that have 3 things in them inside the square root?
Would you combine all of them? Perfect square. Perfect
square. So do you know those perfect square guys that you just finished doing? At least some of them were perfect squares. Remember those guys? You know, they're 1/3 y cubed minus a half y to the -2. You know those guys, right? The same kind of algebra is going to happen. If you can make it a perfect square, then this question, that's actually a bad choice here. This question can then be turned into perfect square, but won't the perfect square and the square cancel out? And you will be left with something that you can just FOIL out and get the answer to. Actually, this is more likely to be x cubed x to the -2, but whatever. So I've just given you a heads up. This is the type of math that you're going to be dealing with in these kinds of questions. So here's my first example. We want to take the curve y equals x cubed. It's going to be rotated from x equals 0 to 2, and it's going to be rotated about the x-axis. Since it's going to be rotated about the x-axis, it has to be either situation 1, which means use this formula, or situation 2, use this one. Which of those two do you think is the right one to use? 1 or 2?
One.
Correct. Isn't everything in x's? That's how we know. So the surface area formula is the integral from a to b, 2 pi f of x, the square root of 1 plus the derivative squared dx. Okay, let's just focus on that now. In this case, from 0 to 2. I like to stick the 2 pi outside, it just gets in the way. F of x, well, if I tell you that y equals x cubed, I'm also telling you that f of x equals x cubed, right? That's essentially what I'm telling you. So we have an x cubed here. 1 plus, the derivative of this guy is 3x squared dx. And 3x squared is 1 plus 9x to the 4. So if we can find this integral, we'll have found what they want, the surface area of that rotated shape. What technique am I going to use for this fella? I need to integrate this guy. How am I going to do it?
U sub.
I'll just do it over here. Would you all agree ugly guy inside square root is a U sub? Pretty standard one. You differentiate with respect to x, you get 36x cubed. 1 over 36x cubed du gets you dx. I guess I just skipped a line there by mistake, but be happy about that's what you get. So this integral becomes 2 pi, the integral of x cubed square root of u times 1 over 36 x cubed du. The x cubes cancel, and that 1 over 36, I'm going to pull it out, and 2 over 36 gets you 1/18 pi. The way my brain works is get all the ugly numbers and fractions and whatever outside, and that way it makes the integration better. It doesn't interfere with it. Does that kind of make sense why that might be a useful strategy, just to keep your life easy? Now, you want to integrate this guy. Would you agree that you have to call it u to the half? Are we good? Right, now, add 1 to the power, divide by the new power. Good grief. That means you're going to do a 2/3 then, right? Well, that and that is going to now get me 1 over 27 pi. I'll write that again. 1/27 pi. And u to the 3/2 is going to be that guy. So I guess I could put the pi on the top. It looks a little bit less work. And the cube root becomes 1 plus 9x to the 4 cubed, evaluated at 0 and evaluated at 2. So we get pi over 27, 24816. Just do this in my calculator. 1 plus 9 times 2 to the power of 4, which is 145 plus 1. It's 146 cubed. Okay, take away, that's nothing. Take away 1 of those, basically. So, take away 1. So you might want to call it 146 square root of 146, take away 1, which is the same thing as that. I think that's probably slightly nicer, but I guess some of you might think that's slightly nicer. Have you noticed how ugly that answer is? I was telling the other class, I had a look at some of the homework questions and the answers. There's an awful lot of really weird fractional answers in these questions. So don't talk yourself out of it. If you ever get a question like 5,370 over 812 pi, right? You're going to look at that and you're going to say, that doesn't look right. But actually, that's the kind of really weird answer some of these guys are equal to. I mean, that's probably not as weird as some, but it's still pretty ugly. Any questions about our first one?
Someone in chat has.
Yeah. What was it they asked? It's better if you tell me. I have to go out and in to read chat.
They're requesting a quick walkthrough of how you chose the surface area form.
Okay. So in the question that we had, which was here, the first thing I go to is I look at what axis are you rotating about. So if you're rotating about the x-axis, it's questions 1 or 2, right? It's these two situations. And then I look at what the information was, the form it was in. And the information was in x's, right? It was everything y equals x cubed, x between here and here. When everything is in x's, you use that one. If you had a different question where you were rotating about the x-axis, right? So maybe you were rotating that guy and you were doing it from y equals 0 to 2, but you're still rotating about the x-axis. Because you're rotating about the x-axis, it would still have to be 1 or 2. But do you see this time everything is in y's? So if it was this question, I'd be using the formula from situation 2. And the one that we just finished doing, everything was in x's, so that's why I would be using the formula from situation 1. I hope that helps. We good? Can't tell. I'm hoping the person who asked is happy.
Their follow-up to that is, so it's as simple as the question feeding you the form.
So by that, if you see a lot of x's, you know it's one. If you see a lot of y's, you know it's the other one. If they mean that, yes, I agree. So let's look at, let's look at this one. The second one I'm going to do involves a square root. We're going to do it from x equals 0 to 4. And it's going to be rotated about the x-axis. And actually, an awful lot of homework questions are situation 1. So why is this situation 1? Well, quick recap. If you rotate about the x-axis, it has to be one of these two. Doesn't this have the form, everything is x's? Everything is x's, you use 1. That's why we know it. So the surface area is going to be the integral from 0 to 4 of 2 pi, this guy here, f of x, 1 plus the derivative of this guy squared dx. Right, this question here, the bit inside the square root is not nice. And rather than me trying to do all my working all the way through and keeping track of stuff, I am just going to focus on one piece of the puzzle. I am going to take this guy and find out what that is equal to in the simplest form I can get it to, right? So, if you're going to differentiate something like this, even if you were going to integrate it as well, wouldn't you probably call it a half power? That seem reasonable? And then, oh darn it, can I call it f of x just so that it works with my formula, right? So if I differentiate this function, you multiply by the power and you reduce the power by 1. So far, so good. Did I miss something? Because this is a chain rule.
You have to multiply by 2.
In this case. Maybe the next time it's times 4 or times 8 or whatever it happens to be, right? 2x plus 1 has a derivative of 2. So the 2.5 cancel, and this guy becomes 2x plus 1 to the half. So you're going to be spending a lot of time doing algebra to try and make this piece as nice as possible, because this is the piece that's causing all the trouble when we have to integrate. You don't really have a lot of problem with this, but you do have with this. Now, if you take this guy and you square him and you add 1, you'll get 1 plus this guy squared. Is it okay for me to write that down, or do you want to see what the middle line looks like? If you square this, do you see that you get that? No more square root. If it helps, if you square that, you get that. Does that help? Now, these two guys, you might think is fine. I don't need to do any more, but you do. You want to make this as style points again, right? You want to make this as simple as you could possibly get it. So what I'm now going to do is I'm going to join these together as a single fraction. So essentially, the number 1 is going to turn into that. It's basically 1 times that guy. Add that. And then very similar to what you did with partial fractions, try to put them together. So what do I now have is I have 2x plus 1 plus another 1, so it's 2x plus 2, all over 2x plus 1. Which means I now know what this entire package is, right? Including the square root. Well, not the square root. But it will be in a minute. Is there anything you can do to this big ugly square root of a fraction that might be of use later on? Is there another way of dealing with this?
Splitting the square root to be in the top and the bottom.
And that is allowed. So now I can go back here, and it's going to be the integral from 0 to 4 of 2 pi. F of x happens to be the original function. This big horrible square root is a square root of that over the square root of that dx. And do you see something really nice has just happened? Is there anything I can do here to simplify this integral?
We can cancel the root 2x plus 1.
Oh, and by the way, I'll stick my 2 pi over there. I've not been doing that lately. And now we have this guy. So do you see that that was the same situation I talked about, right? Where you end up with a square root. Now, if you start with a square root like this kind of guy, 4x plus 1, 1 minus 2x, whatever it is, you're going to end up with something that looks like that at the end, right? I'm going to do a dot, dot, dot this, but couldn't you do a u sub on this if you wanted to? Or you could rewrite it as 2x plus 2 to the negative a half, and couldn't you use the linear shortcut method to get the answer that way? Oh, not negative half, sorry, plus a half. Yeah. Use the linear shortcut method. Are we good? Right. Now, third situation is that you are going to end up with a perfect square inside the square root, right? And the kinds of questions that generate that are the exact same questions that you did in arc length. You remember those weird fractions where one was positive power and the other was negative, that kind of thing? That is a good example of where that might happen. So this is question 5. And we are still on situation 1. I haven't bothered to count, but at least half the questions are going to be situation 1, which kind of makes sense. Don't you typically take functions and rotate them about the x-axis? And the functions are always, not always, but a large proportion of them, aren't they y equals x cubes and sine x and whatever? So it's not that unusual that you'd expect so many. And we will eventually, well, tomorrow more likely than today, look at ones where another rotation, right, with y's in it and things, right? Now back to this fella. The surface area is going to be, yet again, number 1. So it's going to be the integral from a half to 1 of 2 pi f of x, the square root of 1 plus the derivative squared dx. And just like I did last time, let's focus on getting this square root thing as pretty as possible. So f of x is 1/6 x cubed plus 1/2 x to negative 1. Do you see that 1 over 2x is a half x to negative 1? It is not 2x to the negative 1, which is a common mistake. It's a half. If I cover up the x, does the half look a bit more noticeable now? Right, now, why did I change it to a negative 1 power?
It's easier to take the derivative.
Right, we need to use the power rule, right? So square roots have to become a half, and 1 over x cubed has to be x negative 3, things like that. So I'll take its derivative, multiply by the power and reduce it by 1, multiply by the power and reduce it by 1. Now I'll take the derivative and square it, which means I'm going to take this guy and multiply it by himself. If you do f, you get a half x squared times another half x squared. That's pretty obvious, 1/4 x to the 4. What is less obvious is what the O gets you. 1/2 x squared times -1/2 x to -2. What on earth do you get when you multiply those two guys together? And you've seen this before.
-1/4.
Great. And if you go the other way, you get another -1/4. And if you finish off, these two guys at the end get you +1/4 x to -4. If I then move and say 1 plus this guy, you will get this fella plus 1/2 plus this guy. And you might say, wait a minute, how come that's a plus? Well, here goes. These two combined give you -1/2. But if you add 1 and -1/2, don't you end up with +1/2? So far, so good. Do you recognize that this has got 3 terms and therefore better be a perfect square? And when we had perfect squares, wasn't there a kind of, don't worry about the middle guy, it'll sort itself out? There was a way of telling what each piece would be. Okay, 1/4 x to the 4. Won't that get me 1/2 x squared? What will the 1/4 x to the -4 get me?
1/2 x to the -2 power.
Agreed? And I'm pretty sure I mentioned this, but if I didn't, I'll mention it again. Do you notice that the derivative f dashed of x and this guy are almost identical, except this is a plus and that's a negative? If you've done 2 or 3 of these, you will discover that that pattern tends to exist every time. That the derivative on its own ends up looking very like these two terms, but just with a plus. And that's also a good sign that you've done the whole thing right. Now, if you stick this fella inside the square root, which is kind of the last bit of the calculation, what you're basically doing is finding the square root of that guy, right? Well, doesn't a square root cancel a perfect square? And now you're looking at this guy. So over here, the surface area is 2 pi, the integral from 1/2 to 1, f of x, right, the untouched function, which is 1/6 x cubed plus 1/2 x to -1, times this fella, which ends up being 1/2 x squared plus 1/2 x to -2 dx. Now, although that isn't very pretty, at least it doesn't have a square root in it. Agreed? Now, I'm not going to finish this question off, but we'll talk a little bit about what you would do. What would you do next to try and get this integral? Because really the way it's written is not very helpful. What would you do?
Distribute.
Yep, do a FOIL on it, right? And I'll just do the first one. That guy times that guy gets you 1/12 x to the 5. Can you imagine getting a whole load of other equally ugly guys? But at least, aren't they just powers of x? So that would mean power rule with some really ugly fractions and really ugly powers of x, probably, occasionally at least. But doable. Then you plug in 1 and you plug in 1/2, and you'll get 417 thirds as a pi, right? Don't expect 2 pi off these questions. Don't expect pretty, right? But, you know, if you do it right, the ugly answer will be the right answer. Are we good? Right, I did this with the other class, so I want to do the same thing with you. We're kind of jumping ahead a little bit, and this is a question that comes a little bit later in this section. But I want to do it right now because it's kind of cool. I want you to imagine that you take the function 1 over x and you rotate it about the x-axis. And you would make what's called Gabriel's horn. Oops. Not very good. Can you imagine why it may be called Gabriel's horn? It's kind of like a horn, isn't it? What's different about this question? We are not going to do 1 to 7 or 1 to 10 or 1 to anything. We are going to do it from 1 to infinity. And we are going to find two different things. The first thing is a harken back to something we've done in the past. I want to find the volume of this shape, right? Its volume. It's the integral from 1 to infinity, right? Because we're going all the way to infinity. And I'm going to do the pi f of x squared. You remember the disk method for rotating about the x-axis. So in this case, it's going to be pi, the integral from 1 to infinity of 1 over x squared. And I'm going to then do that. And that has to be turned into that. So far, so good. Do you think this particular shape is going to have an infinite volume or a finite volume? What do you think your gut feeling is for Gabriel's horn? Infinite volume.
Finite.
Finite, you're right. Now, what is kind of cool about this question is, doesn't it also require us to use improper integral, right? So if you want to do an infinite one, wouldn't you have to do this t goes to infinity trick? And again, for the same reason I've done it 100 times before, which is an exaggeration, don't you have to call things negative power so you can integrate using the power rule? So it's going to be pi times the limit as t tends to infinity, add 1 to the power and divide by the new power, evaluated at x equals 1 to x equals t, and then I'll do style points on it. So it's now going to be the limit as t tends to infinity of negative 1 over x, evaluated at 1 to t. And that's going to be the limit as t tends to infinity of negative 1 over t. Take away negative is add 1. Okay, since I'm running short of room here, brute force, won't 1 over infinity be 0? And 0 plus 1 is 1, and 1 times pi is pi. The answer is that it has a really nice volume. It's a finite volume. It's about 3.14 gallon, right? That kind of thing, right? For 3.14 cubic centimeters, I guess. Whatever units you happen to be measuring x in, right? Yeah. Okay. So now we are going to do the surface area. So if you could make Gabriel's horn, and can you imagine that I turned it upside down, couldn't I pour pi cubic centimeters into it and it would fill it up? I am now going to paint the outside of it or cover it in material, right? So I'm going to find the surface area. What is your gut feeling? Do you think the surface area is a finite number, or is the surface area infinite? What's your gut feeling? We are not going to let this go by. I'm leaving this for a second. We are going to have a class vote. Stick your thumb up if you think that the surface area is infinite. Give me a thumb vote if you think it's going to be infinite. Oh. About half of you? Well, just because I'm waiting doesn't mean it's right. I'm just waiting till you finish. Right, about half of you. Give me a thumbs up if you think it's going to be finite. It's going to be a number, whatever that number ends up being. It's about a 50-50 split, very roughly 50-50 split. I'm not going to tell you. We're going to find out. Well, it's still situation one. Right, it's rotated about the x-axis. Everything is in x's. I know it's 1 to infinity, but it's still x's is 1 to infinity. So it's the integral of 2 pi, the integral from 1 to infinity of 2 pi f of x, the square root of 1 plus the derivative squared dx. Okay, so we'll do the working at the side. There's f of x, which I'm going to call x to negative 1. So if you differentiate it, you multiply by the power, reduce the power by 1, and then style point it. If you do the derivative squared and you add 1, you'll get 1 plus this guy squared. A negative 1 over x squared times itself is a positive 1 over x to the 4. This guy needs to be joined to the number 1. Which means it's x to the 4 plus 1 over x to the 4. The square root of 1 plus the derivative squared is the square root of all of this. And if you take the square root of the top and the bottom separately, what you end up with is this guy on top over x squared on the bottom. And no, you cannot call that x squared plus 1, even if you want to. You're not allowed to because it doesn't work. So the surface area is 2 pi, the integral from 1 to infinity of f of x times that guy. Which, if I combine the x's on the bottom, we are trying to find the integral of this guy. This particular integral you cannot do algebraically, but I can do a comparison test. Right? So let's do a comparison test. X to the 4 plus 1 over x cubed behaves roughly like x cubed over the square root of x to the 4. Would you agree if x is million, billion, trillion, wouldn't a million, billion, trillion to the power of 4 plus 1, wouldn't the plus 1 make no negligible difference? It behaves like it. Now, that guy is x squared over x cubed, and that guy is 1 over x. What do we know about the integral from 1 to infinity of 1 over x? Does it converge or does this diverge? What does that guy do?
Converge.
Natural log of x between 1 and infinity. Basically, natural log of infinity, this is a shortcut. Take away natural log of 1. Do you see it's infinite? Take away none, it's infinite. Diverges. Right? If you do the little test, remember the x to the p test. If p is bigger than 1, it converges. But if p is less than and equal to 1, it diverges. Maybe you put the equals in the wrong one. Which means that this is infinite. And obviously 2 pi times infinity is not going to hurt it. Still infinite, right? So how on earth could you get a shape who you can fill it up with pi cubic centimeters of paint, but you can't paint the surface? It's like a contradiction, isn't it? Yet mathematically, this is true. So it gives us a little insight into how weird infinity is. And I did an analogy, I think it might work. Do you know that black holes distort space-time? So if you imagine a black hole, it might very well look like Gabriel's horn. Theoretically, if it was a massive black hole, wouldn't it be crunching space to singularity? That means that a black hole can have a finite volume. And can you imagine in space there's a little black hole there? Can't you put a cube around it and the black hole is inside the cube? So that means the black hole has a finite volume. But if you look at the way it distorts space-time, couldn't it at the same time have an infinite surface area? So it's not a contradiction in the real world either. It's just that we have to do very special situations in the real world, even to get a visual idea of how something like that could even exist. And I told the other class the same thing, so I'm going to tell you this. We should keep this a secret from non-calculus students, because if they do find out about it, it'll scare them off and they won't want to do calculus. But you're comfortable enough now with infinity to realize that weird things can happen with infinity, right? You're getting a little bit more comfortable the more you deal with it. And so, as strange as this may seem, it kind of could happen, couldn't it? It could be true. Well, it is true mathematically, right? Okay, so I don't know if I asked you to say hi yet. I don't think I have. So you want to say hi? And I'll then say bye-bye. I'll hang about for anybody who's got homework questions. But say hi before you go.
Thank you.
You're welcome. Okay, anybody got a question from the three that are left?
Yeah, I had a question about the 8-1 homework on specifically number 10. 10 and 11, those two kind of threw me off.
Okay. Have you got, can you tell me what 10 is? It'll save me having to go out and in.
Yeah, 10 is finding the length of an arc to the curve from points P to Q, and it's y equals 1/2 x squared, with point P being -9, 81 halves, and then point Q being 9, +9, 81 halves.
Okay. So this is the function, right? So the arc length is the integral.
And I can't see your like.
Oh, sorry.
Yeah.
Let me. I could see it. I don't know what you can see. Right. So it's the integral from a to b, and it's only this piece of the arc length, right? So it's a kind of, it's doing double duty, this piece, isn't it? It's used in arc length, and then this piece of it and some other stuff is used down in space. Let me just rewrite that again. It's the square root of 1 plus the derivative squared.
Okay.
Right. Dx. Right, in this case, from negative 99. Right, because I can tell from here. If you differentiate this guy, don't you get x? So it's the square root of 1 plus x squared dx.
Mhm.
And don't you then go looking at tables for this guy? And whatever the thing is, you evaluated to x equals 9 in negative 9.
Oh, yeah. I was just confused. I'm like, I didn't know what to do after the square root
1
1 plus
plus
x
x.
squared.
Some integrals you can't do anything with because they are. I mean, technically we could. I could do an x sub, in which case x equals secant theta, right?
Mm-hmm.
And half an hour later I get the answer. But in a question like this, we just go looking at the tables. The tables would have a guy that would look more like this.
Mm-hmm.
But all that means is A is 1 and U is
And
X.
U is X.
And you can do it. And you're still going to have some really weird things. I can't remember exactly, but I think it's got something like the natural log of a secant U plus a tan U or something like that. And it's got weird stuff, right?
Uh-huh.
And so you're just going to plug in 9 and negative 9 and hope to God that it is nice. But if it's not, there is nothing wrong with secant 9 plus tan squared 9 as being an answer. I mean, as an exact value, that is allowed.
Okay.
And if they wanted it as a decimal, because they may have said to 2 decimal places, then it'd be a totally different approach.
Yeah.
Wouldn't
then
you just
like, plug it into the calculator? Right?
exactly, and then
Okay.
do it to 4 decimals? Right. So 11 now. What did that look like?
11 was also from one point to the other. It was x squared equals y minus 8 cubed.
Oh, x squared is y minus 8.
Yeah, yeah. Is y
Cubed.
minus 8 cubed, and then point P is 1 comma 9, and point Q is 8 comma 12.
Right, so I can do this in terms of x or in terms of y. The way I'm looking at this, I think it's more helpful to do that.
Okay.
So the arc length formula is going to be from y equals c to d, the square root of 1 plus the derivative squared, but dy. And this guy here is basically the g of y fella, right?
Okay.
And this is the c and the d.
C and D, okay.
So it's going to be from 9 to 12, the square root of 1 plus. Now, you're going to differentiate this fella and then square it. Right, if you differentiate it, it's a power rule. And so it's 3 halves y minus 8 to the 1/2 power. Technically times 1, but I'm not bothering about that, squared. So it's now the integral from 9 to 12 of the square root of 1 plus 9 quarters y take away 8. If you square each term, that gets you 9, that gets you 4, and a 1/2 power squared gets you a y minus 8.
Okay.
And then I have 1 plus 9 quarters y times, oh God in Himmel, that's 2, take away 18 dy. And that becomes 9 to 12, 9 quarters y, take away 17 dy. So we get to there. And I would suggest probably a U sub.
And then just solve from 9 to 12.
Yeah. Once you
And-
convert it back to the Y's.
And could you also, like, for example, it was originally x squared equals y minus 8 cubed. Could you just like add 8 and just do cubed root
If you
also?
if you want to go that road, you have to be a little bit more careful about the order that you do it. So cube root to both sides gets you this.
Mm-hmm.
Add 8 to both sides gets you this.
Mm-hmm.
And that's the guy you're going to differentiate, square, and add 1. But I think that is really ugly, and I'm not sure that the integral that you get is doable. There is,
Oh man.
right? So sometimes both ways work, and that's fine.
Okay.
And sometimes you can only choose one of the two routes, because the other one, you can set it up, but you may end up with an integral that you can't do.
Okay, so yeah, I'll probably just stick with the x equals y minus 8 to 3/2 then.
For this one here, you'd stick to that one, yeah.
Yeah.
That doesn't mean there are not some questions out there where you could go the other road. You know, there's no easy way sometimes to tell until you're halfway through, and then you realize that you're kind of in a hole and there's nowhere to go.
Okay,
Okay.
well, I didn't have any questions other than that, so thank you very much, Mr. Robertson.
You are welcome. Have a nice day.
You too. All right, good luck, Matthew.
Okay, Matthew, what you got for me? Matthew, hi. Last time, I'm going to go then.